Today we're going to talk about thyristors. So thyristors are a class of semiconductors. A thyristor can only be fully on or off. A transistor can lie in between states, and in between on and off states, that's what it works as an analog amplifier. A thyristor is unsuitable as an analog amplifier. It's useful as a switch. Thyristor usages, they're used for power control circuits, usually AC currents, used for motors and heaters, lights, etc. Electronic switch that can rapidly turn on and off a large current to a load. If we look at the layers of doped material, we started off with a diode. A diode had two layers. It had N and P doped material. We had the NP junction. Transistor had three layers and had up to three layers of alternating material, N or P. So we had NPN transistors and PNP transistors. A thyristor has four layers. So it goes NP, NP. The first thyristor we'll look at is called a silicon controlled rectifier, an SCR. And it's a rectifier that we can control when it turns on and off. So if we look at the doping here, we got a PNPN junction, and what it is they've taken two transistors, they've taken a PNP transistor and NPN and tied them together. And so if you take a look at their material, they put them together, and this is the equivalent. So it has four layers of material. The pins are the gate, the anode, and the cathode. So this is the symbol for a SCR. It's basically a diode with a little gate attached to it. SCR operation. We got a trigger voltage, a pulse on the input of the gate causes the diode to conduct. The trigger voltage has to be higher than the SCR's forward breakover voltage called VBR. So that's the threshold voltage. When the voltage gets higher, this SCR will latch on. And it'll continue conducting until the anode current drops below the holding current. So on the anode, it has a holding current, and it'll, as long as that current's going through it is greater than the holding current, it'll keep conducting. If we take a look at an SCR circuit operation, this is for DC operation. Whoops. What we have is we have our V plus up here, we have our ground, we have our SCR, and the main current is going to go through here and through our load. The load can be here or it can be on the top. It doesn't matter. So we have a switch here. When we push the switch, it's a push button switch. We get current and voltage coming into here, turns on the gate, and then it starts conducting. This is a normally closed switch. What will happen is that once you turn this SCR on, it's going to stay on. And the only way to shut it off is to stop the current, and you have a push button switch here which will break the circuit and stop the current. So the problem with this is that you need a big switch here, right? So if you're running current this way, you're going to need a big current to turn switch to turn it off. For AC operation, it only passes the positive cycle. It's a diode, so it rectifies it. We only get the positive cycle. And if you tried to run this on an AC circuit, it would reset on each negative cycle. You can kind of think of this as almost a programmable rectifier. Is what you could do is you could turn this, hook this up to a logic circuit, and that would tell it when to turn on. SCR Specs. Vmax is a maximum peak inverse voltage that we can put across it. I total, continuous current in RMS units. So that would be continuous operation currents. Imax is the maximum or peak current. So you can have a continuous current running and then maybe you're going to peak a little bit. IL is I-latching. It's a latching current for the gate in milliamps. So it's the minimum current to keep it in the latch state. IH is the anode holding current to keep it latched. VBR is the breakover voltage. So that's the voltage at the gate to turn on the SCR. Typically they're about 4 to 5 volts. Also called VBO and VBF depending on the manufacturer. If we use an SCR for a light dimmer, what we'll find out is that we'd adjust R2 and C1 would trigger the the gate, and the output is shown in red here. Only the positive cycle is affected. So what would happen is that this provides a delay. So what happens is we get a voltage here. We're going to charge up this capacitor, a little bit of delay, and then it's going to trigger. And then from here on, we're going to have our voltage. Right? So over here, we do the same thing. When it goes negative, the current stops, turns off, and then the cycle starts over again. And what we can do is vary the amount of energy that's going to that lamp. So if we had it turned on here, we'd have a full half cycle. That lamp would be the brightest it could in this circuit. And then as we increase the RC time, we're increasing the delay, we could go all the way up to about here. So we can get from a full cycle to about half cycle. Now, there is a problem with that. And what happens is that if we look at the circuit, when we charge up a capacitor, it has a slow rise time. And SCRs don't like that. What happens is that they're going to have trouble turning on. They could overheat. They could have all sorts of issues. So what we can use is what's called a DIAC. It's a diode for alternating current. This is the symbol. It looks like two back-to-back diodes together. The DIAC will fire when a threshold voltage is reached. So here we have our capacitor charging. It's got the slow rise time, which we don't like. And all of a sudden, we have a DIAC in series with the gate. And when it reaches its threshold voltage, the DIAC fires, and it lets the voltage through. So we get this nice, sharp rise time, which SCRs like. So we got a nice clean gate voltage on here. So rather have this slow rise time, we get a nice rising edge. The next thyristor we're going to look at is called the silicon controlled switch, SCS. The problem with SCRs and DC circuits is you need a big switch to turn it off, right? So what we find is you need a big switch here. And the whole point is if you need a big switch here, why even bother using this circuit, right? Just put a switch in. So an SCS is an SCR with an off gate. And what they actually did is took two SCRs and put them back to back, right? So here's one SCR here. We have our anode, our cathode, and then we have a tied to here. Then we have our anode gate and our cathode here. So if we were to look at that as a transistor, it looks like this, is that we put a PNP transistor, this becomes the cathode gate, and then we have an anode gate over here. And this is the symbol here. It's just basically an SCR with another gate on it. So if we look at a silicon controlled switch circuit, what we have is an on switch, very low current. You can just put a tiny switch on here. It's a push button on, right? And then we also have an off switch, which again is just a very inexpensive switch here. All the main current is going through the SCS. So if we want it on, we push this button, that latches on. Want it off, push this button here, and it turns it off. And now we can have a fully programmable control system here. This could be run by digital logic, right? Turn it off, turn it on when we want. Now for AC circuits, what we need is a TRIAC. A TRIAC stands for Triode for AC Circuits. And TRIACs can pass current in both directions, and this is where they've taken two SCRs and put them back to back here. Right, so we have one SCR for this direction, another one for this one. We tie the gates together. We have anode 1, anode 2. The symbol for an SCR is you take a DIAC and you put a little gate on it. Right? And they're just called anode 1 and anode 2. Doesn't matter. There's no polarity. They're just two different anodes. Sometimes they'll call, instead of anode, they'll call it MT1 and MT2. Triac conducts on both the positive and negative cycle. So what we see here is that this is an SCR and SCS. They just basically conduct on the positive cycle. Over here on a triac, it conducts on the positive cycle and on the negative cycle, right? And we can put control circuits in that we can control how long it turns on. So triacs are suitable for light dimming circuits, phase control circuits, AC power switching circuits, AC motor control systems, and etc. So here's an example of a triac circuit, very similar to the SCR one we had. We have a variable resistor and we have a capacitor. We have a RC constant, so we're going to be doing charging. When we get an AC signal, it's going to take a little while, a delay here before it turns on, depending on how big this R is. A DIAC's going to fire and it's going to turn on this SCR. And this is a circuit used by your home light dimmer. So, speaking of light dimmers, most people incorrectly think that a light dimmer is just a big potentiometer. If you use a potentiometer in this manner, it's called a rheostat. And here's an example of a rheostat over here. It's just a big wire-wound potentiometer, right? Now, the problem is if you had a 100-watt light bulb, you'd need a 100-watt rated rheostat. Now, 100 watts is a lot of heat, which means that if you were dimming your light, turning this down, this would mean most of the energy would be sent through this resistor. It would just be a series circuit, and you'd have to dissipate 100 watts. 100 watts is equivalent to having a soldering iron in the wall. So if you had a soldering iron in the wall sitting there for an hour on the end, you would have a fire hazard. So we actually, light dimmers use triacs. An old school DIAC is called a neon lamp. So this is an example of a neon lamp. It's very small, probably as big as your thumbnail, and they have 2 electrodes, and it's in a little envelope of neon gas. And at a specified voltage, the gas breaks down and starts conducting. Right? You often see little lights like this inside electronic devices in the 50s to the 70s, and it's little neon lamps being used as DIACs. I believe that the breakdown, it's kind of an obsolete technology or forgotten technology now, but you used to be able to get these in all sorts of different voltage ratings. Now I think I looked it up and you can get it, you would fire at 90 volts and then it needs about 60 volts to keep conducting. So that's about it for thyristors.